Part 2. The Koenigsberg Bridge Problem. Koenigsberg was a Prussian city with 7 bridges. The island at the center of this map has 2 bridges above, 2 bridges below, and 1 on the right. There are 2 more bridges on the right half of the map. Could you take a walk so as to cross each bridge exactly once? This was a recreational problem, I suppose, in Euler's time. He solved it by proving no such tour exists. The city and its bridges can be modeled as a graph. Each landmass is represented by a vertex. Each bridge is represented by an edge. When you take a walk on a graph, you enter each vertex the same number of times you leave, except perhaps for the start and finish. So a tour has an even number of edges incident with each vertex of the graph, except for the start and finish if they differ. Yet the Koenigsberg graph has 4 vertices with odd numbers of incident edges, at least 2 too many. Euler's analysis makes it easy to decide whether a given graph has a walk that uses each edge exactly once. A variation on this problem involves a walk that uses each vertex exactly once. It's easy to find such a walk in Koenigsberg, but the problem is more challenging in larger graphs. These 2 problems, enumeration of regular convex polyhedra and the Koenigsberg bridge problem, are important to graph theory in retrospect, but graph theory didn't really get going until the 19th century, largely driven by the effort to solve a single problem. When a map is printed, territories that share a border get distinct colors. This makes it easier to read, but non-adjacent territories may have the same color. This example has 6 territories and 4 colors. If you try to conserve colors, you find that 3 or 4 are enough for most maps. This example requires 4 colors because the 4 territories in the lower left are pairwise adjacent, so each territory must have its own color. But no one has ever constructed a map that requires 5 colors. In 1852, an English student asked his mathematics professor whether 4 colors always suffice. Long story short, over 100 years passed before it was confirmed that 4 colors suffice. The proof is so long that we rely on computers to check it. However, it's easy to show that 6 colors suffice. A map can be modeled by a graph where vertices represent territories and edges represent bordering pairs of territories. Such a graph is planar, like the graphs of convex polyhedra, though there are differences. The proof goes by induction on vertices. A key idea is that if some vertex v meets fewer than 6 edges, then we're done, for we can remove v and those edges, leaving a smaller, planar graph. Invoke the inductive hypothesis to color that graph with 6 colors, then replace v and its edges, and give v a color not assigned to its neighbors. In case you're not familiar with proof by induction, here again is the idea. Suppose every planar graph has a vertex that meets fewer than 6 edges. Then, from the given graph, we eliminate such a vertex, and from the new graph eliminate such a vertex, and so on, until the graph is so small that obviously it can be colored with 6 colors. Then we reverse the elimination of vertices, reintroducing them one by one, and assigning colors as we go. Because each vertex had at most 5 neighbors when it was eliminated, a 6th unused color is available. Our goal now is to show that indeed every planar graph has a vertex that meets fewer than 6 edges. We use again Euler's polyhedral formula and 2 more relations among v, e, and f. Maps, however, are not assumed to be regular. There are no parameters p or q. Let d be the smallest number of edges some vertex meets. Then d is like parameter q from our study of polyhedra, except that now vertices may have different values q. Our d is the smallest q. Then each vertex meets at least d edges, and each edge meets at most 2 vertices. If we visit each vertex and record its incident edges, then the list has at least dv entries, and each edge is listed at most twice, so the list has at most 2e entries. So dv is at most 2e. Now each edge meets at most 2 faces. Let's assume each face meets at least 3 edges. If we visit each face and record each edge, the list has at least 3f entries. Each edge is listed at most twice, so 3f is at most 2e. then v minus e plus f equals 2, assuming the graph is connected. That's the Euler polyhedral formula. We apply our two inequalities, so e times 2 over d minus 1 over 3 is at least 2. Now 2 is positive and e is positive, so 2 over d minus a third must be positive. That is, d is less than 6. Some vertex meets fewer than 6 edges. The 6-color theorem is complete, assuming each face meets at least 3 edges. A rigorous proof would deal with the other case, perhaps by showing it can't happen. You can read about this in textbooks like the Introduction to Graph Theory by Douglas B. West. He also keeps a list of open problems in graph theory you can find on the web. Now these coloring theorems may not seem to have much practical value, but graph coloring comes up all the time in computer science, social sciences, operations research. It's a model for allocating scarce resources in the presence of pairwise conflicts. Those resources could be meeting halls, computer memory, or counselors. Graph coloring was one of CARP's 21 NP-complete problems. It has a reputation for difficulty. It's NP hard even to decide whether a planar graph can be colored with 3 colors. Of course, 4 colors suffice, that's the 4-color theorem. In the case that 2 colors suffice, it is easy to detect. But it is very hard to decide whether 3 colors suffice. And in the unlikely event that you find a decision algorithm that works efficiently on the whole class of planar graphs, you will be famous. So we study special classes of graphs, and we study relationships among coloring statistics and other graph invariants. My doctoral thesis involves coloring of interval graphs. These arise in computer science and bioinformatics. It's known already how to color them optimally, but there are more challenging variants of the coloring problem that are not as well understood. That's all for now. I've answered the question, what is graph theory? My name is David Smith.